Opposing Gloves here, and today we're going to talk about sidebands. Now, we talked about modulation index, and that's basically the amount of modulation you're allowing to happen. So it's controlled by the volume, essentially, and we know that if we turn our modulation index up, we get more sidebands. However, sidebands are derived from ratios. Now, there's ways to calculate these things. There are ways to do all sorts of things, and we're going to talk about the basic way to calculate them, and then we're going to look at a couple of patterns, because after this, it's really about building a sonic vocabulary. You pretty much understand why things happen the way they do. Sidebands are pretty much the last thing, and this is the part that tends to get the most technical. So we're going to sort of brush over it, because knowing exactly how to calculate sidebands isn't exactly the most useful thing for the synthesizer person. It is more useful to know some of the patterns that emerge so that you can begin to manipulate things in a way that will be beneficial to you. So right off the bat, we are going to look at, I'm going to use FM8 in this video just because I haven't really used it that much. And we're going to look at, so these sidebands. Now, if we take F, operator F, and it's outputting a sine wave at a ratio of 1. Now, the thing about FM8 is its ratio is based on a ratio of 1 instead of a ratio of 2 like in Citrus. So FM8 goes ratio 1, so up an octave's 2, up an octave 4. So it starts out at 1 though. I don't know why Citrus starts out at 2. It's a little unusual, but I'm sure there are reasons beyond what I know. So here I have just a basic sine wave, and if I were to FM it by itself, so feed it back into itself, we notice that we get a saw wave series. And you might naturally ask the question, where do all these sidebands come from? Let me open it up on the spectrum. We have all these extra sidebands. So where are they coming from? Well, they are coming from. So we have a fundamental. We know what the fundamental is. So if you take the fundamental, and then depending on your modulation index, so depending on how much modulation I say allows to happen, and you can see the spectrum represented up here. Depending on that, actually, if we come over here to the spectrum view, you can see the waveform that will be produced. And so what happens? So you have a modulation, so you have your waveform. In this particular case, so it will be I'm going to give you a little math equation right now. I'm not going to write it out. You have, so the sideband produced will be equal to the carrier frequency plus or minus a number times the modulating frequency. So it would look as a W subscript SB equals a, let me open up like Notepad or something. It should pop up like the magic it is. Search Notepad. There we go. So it'll look like wavelength sideband will equal, and then it will equal the carrier frequency. So wavelength, I'm going to make it a W, a big W. So wavelength sideband equals wavelength carrier frequency plus or minus, but pretend those are on top of each other. So plus or minus the wavelength, some number, so some number times the wavelength of the modulator frequency. So WM, or the frequency, I should say, the frequency of the modulator, frequency of the carrier will equal the sideband plus or minus this number. So where do these sidebands come from? So let's say we've got 100 hertz. Well, let's go back to the equation. So let's say we have 100 hertz. So our wave 100 hertz. On our zero integer, it would be called the zeroth series. So to calculate our first integer, we calculate 0 first. So our wavelength times 100. So we have 100 for our carrier plus or minus n, which would be 0, times the wavelength of our modulator, or I keep saying wavelength, frequency of our modulator, that would be 100, and we multiply them together, you get 0, so all would be left was 100 for the plus and minus, so you just are left with 100, and both times. However, the phase, this isn't the whole deal right here. There's some unusual deals with phase that go on in amplitude that I'm brushing over, because I just want you to get a general idea of where these sidebands come from, and from here on out we kind of just need to have a bunch of examples, and then the real key comes from modulating things and building up a sonic vocabulary. understanding all this other stuff is sort of, I found that this is the point where like I start getting diminished returns as far as my ability to intuitively mess with FM. So we have wavelength, sideband, blah, 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 blah. So that's the zeroth series. The second series, so now we just put in a 1. So wavelength times the carrier plus or minus 1 times our wavelength or the frequency of our modulator. So it'd be 100 plus or minus 1 times 100. We'll get 2 answers. One will be 0, one will be 100. We add it, and you'll notice as we move on to the second and third, this series should be infinite. It should go on for forever. However, we know that our signal is band limited. So we run into some interesting things. Some FM synthesizers will allow things to be aliased back into the spectrum, and so you'll get aliasing the higher your ratio goes, which you'll very clearly see happen in the next video. Other things will try and oversample those things out so that they can be represented in your signal, and then it can be downsampled after it's gone through your FM engine. If you don't understand that statement, go watch my Digital Audio Basics FM video. So on this note, this n can be other things too, but right now we're going to leave it as integers to keep things very simple. Okay. And again, I'm ignoring phase and amplitude information with an equation like this. It does not come out like so easy because the carrier frequency has its own phase and amplitude relationship, and the modulator frequency does too. And so the way they sum is different. Now, if we get a negative number out of here, I don't believe I've said this yet, but if we get a negative number out of our equation, it just gets flipped into the spectrum. So what's important about this jazz? Well, one of the things you can see here is when we take a sine wave and we modulate it against itself, we feed back it into itself, we get a saw wave because it produces every harmonic according to our equation, and you can see the amplitude thing, which I didn't really touch upon because it varies quite radically. If I open up Citrus, Citrus goes about it a very different way, and Citrus has an oversampling option, which also changes the game for the way Citrus produces something. So you literally get different timbres just because we're using a different tool. So I'm going to turn oversampling up I'm going to put on default, turn oversampling up, and then you see it's much louder because we have oversampling capabilities. If I went to the 50% they were at, and it's just a totally different ball game. So this equation is a really rough equation to give you an idea of where things come from. The real power, the real tool comes into play when you start messing with your sonic vocabulary. So from here, the next video is going to give you an example of the pitch, so the ratio slowly rising. And then I'm also going to then start doing particular configurations in things that produce particular results. Because if you could build those up in the correct way, you'll be able to do some pretty complex decisions intuitively. And that's the goal. The goal is not to teach you like all the math behind FM. That was never the goal. So yeah, if you have any questions, let me know. Subscribe and have a blessed day.
Opposing gloves. Reversing.